Our next speaker is Daniel Bennequim from Jussieu University, from Institut Jussieu. Thank you very much, Daniel. He will talk about tuples and stacks for understanding semantic functioning of deep neural networks. Thank you.
Oh, thank you. I thank the organizer to invite me for presenting this work. Okay? And I apologize because I'm not able to come in Miami. And of course, it would have been much better for exchanging ideas with you. Okay? But I will try to come also to other session for this discussion. Okay? Perhaps you tell me you will tell me the program, okay, of the night session. Okay? And also I apologize for my English, okay? And also for perhaps the material I will present, which is certainly too late. Do you hear me correctly?
Yes.
Yes, okay. So I will I do, yes. Okay. So I present a joint work with Jean-Claude Belfior, which is an engineer in Huawei Paris, and in fact the director of the laboratory for wireless communication. And the source of the work I will present, which tried to detect the common structure in neural network, and mainly why they are able to do some semantic, and we can develop that. There are three sources. Yeah. Historically, it is the second one in this, which was the first. Yeah. But I begin with the one, because it's perhaps closest to the result. Okay? Is that a very long collaboration with Alain Berthoz, which is a neurophysiologist, especially on human movement. Okay? And we suggested, some years ago, that for controlling and generating movements, okay, in space, okay, we use something like toposes with geometries. And the second one, which second work, okay, was about information in general. So information is mainly known through the statistical version from Shannon theory. Okay? And it was also a work with a neurophysiologist, okay? But which shift after that to artificial intelligence, which is Pierre Baudot. Okay? And this work was motivated by understanding the change in vision when you change the nature of the image. And it's here that for the first time, I, for example, began to work with topos, and we discovered that in fact the Bayesian network have a kind of form, and the first invariant given by topos theory is the entropy. So I will present a bit more. And the third work, which is the true reason of the work I will present, okay, is to try to understand the possibility of semantic communication. So it has two parts. One part, which is to understand better what could be a semantic information, which is certainly not totally of statistical nature, okay? And also how we could use networks, okay, that as a natural neural network, okay, to maximize this kind of semantic information if it exists. Okay. So the example is this one, for example. which is the model we had in the head, even by looking at the artificial neural network. Okay, and it is the space for prehension, that is to keep an object. Okay, and neurophysiologists since a long time know this involves at least, in fact, much more, three regions of the brain. Okay? And they are noted by cortical, neocortical region, but in fact, you have also the whole brain, which is involved. But here, because in each of this region has some particular speciality. For example, you have to understand the object. Okay? And if I keep something on the table, okay, I have to understand if it is round, if it is heavy, if it is okay. So, and it is a kind of which I like geometry in general, or the characteristic, okay, of something very particular, which is a rigid object. It could be non-rigid. It's also so you have to express what are these properties, but you also have to express how you configure the hand, okay? And it takes a very great part in the brain, and also how you will move your arm to get the object. So, in fact, the true space where the brain works is made by different pieces, which are interconnected, and now it's well modelized by artificial neural network, which reflects the activity of true neurons. So this is not so far true neurons and artificial neurons when you look at the level of the whole network. And this is the reference here. And in some sense, this gives an insight of a new kind of dynamical system. And this is in this kind of dynamical system that we will work, and are, at this moment, poorly studied. Okay? That it's known that dynamics is mostly made for asymptotic behavior. And it's true that the neurons react so quickly that in some sense they go to attractors or something before they change again. So they could be modelized by something like asymptotic dynamics. Okay? It's very quick, but also you have now the connections which are activates in the brain and which are as a connection between different layers in artificial neural network, and which are much better modelized by something which is transient dynamic. Okay? That is not asymptotic at all. It goes from point A to point B. Okay? You enter data and you go and answer to a question. Okay? So this kind of system, which of course organize both, is not so well understood in general. Okay? So not only for neural network. And yes. So this is the appearance of this geometry for movement, because that we suggested, okay, which are made by a coherent collection of maps between sets, okay, and the model which we had in the head when we think about that is this object that the mathematician Grothendieck introduced first for the need of algebraic geometry, and then for many other things. And one of the main points here in this topos is that you have a kind of localization. Localization of geometry, for example, because you have different geometrical space in the ordinary sense here, which covers the physical space, that is related to physical space, but non-trivially. And examples are here. Space of postures, for example, for the arm or the hand, okay? A space also for the body, a space for also imagined motion, okay? And they involve different regions in the brain. Okay? Stacks is a technical name, so there's a very precise axiom, okay? That, for example, Carlos Simpson knows very well. Are made by a collection of such spaces, okay, which are organized between themselves by category, okay, which is kind of the base of these stacks, okay, and which generates a topos that we'll present in few minutes. Okay. And this is a network in some sense of different areas. And the second origin was this idea from Bayesian network. Okay. And in this case, what are the local sets or the analog of the local? They are the random variables, in fact, in the Bayesian network. Okay? But Bayesian network work not only from values of variables, but you are exploring a lot of probabilities. Okay? And the way you explore these probabilities is mainly through a function of probabilities and variables. Okay? Which, for example, what is the information content obtained when you look at one variable, okay, if the probability law of the system is under this state. And that we formalize with Pierre Baudot, this young neurophysiologist, okay? Also by a category, in fact, because one variable is in general too poor to understand the evolution of the system. Okay? And so you get many variables and you can join the information of this variable. Okay? And now you look at what you get, what you obtain as better information when you join this variable and this variable, for example. And all that was very well expressed by an invention of Shannon, okay, which was this action of variable on function of other variable, okay, and which is, in sense, the mean, because you apply the probability of the function where they are conditioned by. So the heart of this action is the condition. Okay. And what we found is that this is exactly an object, okay, like we saw, for example, the torus of manifolds obtained from the sphere S3 by surgery. And for this kind of object, Grothendieck found that they also have invariants, okay, like the invariance of knots, okay, that we see, but more like the homology of Romanov, because they are precisely named homology. And topos theory was in fact invented to understand the kind of topology of described by homology, especially in algebraic geometry, but it extended to more objects. So what was strange is that if you don't choose special axioms, because that's the interest of this approach, that you look only at this object as a geometrical space as generalized by Grothendieck, which shows that many things that we can do for ordinary space or ordinary topological space, as Admela just showed, can be applied also, because strange objects occur already in algebraic geometry, but after that, they were found in many domains. Okay? So we just compute in some sense. We compute the invariant of this space. This space given by the random variable if the function of them depends on probability. And we find exactly the Shannon entropy and also the Eiger information. So you see here, you have two kinds of objects. This is the variable, which are related. Okay, for example, you consider the join of variable, but some joins could be non-observable, as in quantum theory, and you have the probabilities. So we will recover these two sources in the general theory. So I will describe now what we found with Jean-Claude Belfiore when trying to understand the nature of artificial neural network. And the first thing we observe is that anybody knows that apparently they look like a graph. For example, here you have a source, but you have a kind of recurrence, that is, you have loop, and then you go out from this source. This is not so simple shell, because now to understand the functioning of that with a dynamical system, you cannot only look at the picture like a knot. It is, in fact, you have to develop it in a plane by introducing the time, for instance. And you see now the relation really between this part. Of course, here in some sense, this is the same layer, but this is the same layer at two different instants. So you have an arrow which transmits a kind of memory, and now you integrate new data and you produce new memory and new input. So if you look well, it's a kind of a relativistic system. That is, you have the variable x, y, but also you have the time. It is that. And every graph which are used for neural network, in fact, have this property to be directed when you take the right covering. That you never come in the brain, for example, even if you see in image a lot of loops, it's not true. In fact, you don't have loop. You have a connection between some part at some time with this same part at another time. And now, but this is not very good to represent the dynamic, because on a category in general sense associated to a graph, that is, you follow all the arrows you see, you have no way to express what happens when you have two arrows coming to a point. In fact, it's not totally true, because it was at the heart of the beginning of what Grothendieck introduced as new kind of topology for algebraic objects, but also for discrete objects. And for doing this composition, which is very frequent, in fact, in neural network, for example, you use both your A's and your R, and you join information. So what is the join of information? And it can be represented at the level of graphs by this picture. So this is a naive picture in some sense here, what you see on the graph. But in fact, what happens is not that. You have a point, which is a kind of virtual point, which collects all what happened here. So the states here is the product of the states here. And then you take a copy, and now you can transmit. This kind of topic is a bit technical. I will not explain all of that. But what I said is that. That is, you don't have only a category, you have what is named a Grothendieck site, which is a category plus kind of topology, which is given by set of arrows coming to a given object, satisfying some axioms, which generalize the axiom on the open set. In fact, on the coverings, full coverings on open set by open sets in the topological setting. And they define, this topology serves to define a kind of constraint of the function, which are never true function. They are like section of a kind of bundle, and which form what is named sheaves, if you know this name from geometry and topology. And this product situation is exactly an axiom to formulate, to here precise the sheaf. So what you have in spite of, for example, the RNN I showed before, which look very simple. So I will explain you why to complicate so much. You have this loop. First, you complicate by having a relativistic representation. And now you complicate again, obtaining that, which says that in fact, at some place for the dynamic, you cannot propagate in the graph because you cannot join in the graph. There's no sense. But you can, if you do this topological operation at the level of categories, which gives you this object. For the brain, it's a bit difficult, but for a machine, it's very easy. And in some sense, it is a kind of generalization of trees. There are trees which are attached by leaves, which is a very special structure here. But it happens, in fact, that you can also forget a bit about some complexity of the Grothendieck topology, because what is important here is to understand this sheaves, that is, which represents the propagation of activities in the neurons. And the thema here, the main thema is that activities in the networks is a sheaf over a site, that is a topologized category. But here, this sheaf, this it is a dynamic, in a sense, because it's important to understand what happens for the transition between one object and the other, can be represented. So it is at the level of the topos, because the topos is the technical name, is a name, in fact, for all the sheaves over a site, given site. This is, as understood Grothendieck, the good generalization of sets. All what you can do with set, you can do in this setting. So they are, in some sense, dynamical sets. And it's very surprising that dynamical sets, in fact, have this kind of definition. And it's in particular that you can choose different sites. And here, for the neural networks, in fact, it's always possible to eliminate the non-trivial topology just by introducing one virtual point. Voilà. So it's a matter of equivalence of the topos. So you don't lose the possible dynamics, and you simplify the category. So I'm sorry if even from the beginning, you have something which looks like much more complicated, but in fact, by working, you begin to understand, and taking, of course, examples, you begin to understand that all that has a logic. And in fact, this was also the surprise for algebraic geometry, because as soon as Grothendieck introduced that, by working with Giraud and also people in logic, it happens that this is equivalent, in a sense, to a sort of language, which is nothing more at the level of the topos than first-order logic. And this is somewhat hidden, but it is like that. And here, what is important for us is that we will get this dynamic. And this dynamic, as the dynamic I show for the brain, you have the dynamic in the object. In fact, this is the states of the neuron, but you have also states for the mapping from one layer to the other one, which is given by weights. And the functioning of the neuron depend on the choice of these weights. Weights is just a name for the transient maps, which goes from one layer to another one. And the goal of the network is to learn the dynamic for solving problems. So here I name the main result of this first part. So feed-forward dynamics is what we ask to a network, and it is so an object of this topos that is just a contravariant vector to the category of set from this category. This is a representation of the category I have shown, because this concerns the activities in the layer. Plus, in fact, if you want to describe all the dynamic, you have to include the weights, and the way which appears to be the better to represent this weights along, a priori, along the arrows over the graph, is to have the idea that it is all the incoming dynamics which are in this weight. So this gives also a kind of an object, and the way to represent it is just to forget weights of the past. So this represents the dynamic. And also what is important is that you have a dynamic and the dynamics, which is the learning. For example, the most popular before the new time of LLMs is backpropagation for full supervised learning. And this dynamic, which could be something different, in fact, is exactly what we hope. That is, it is a kind of natural transformation. That is, it is totally compatible between from the source and the goal when you learn, and they are themselves arrows, but they are arrows of secondary level, of second level. They are arrows of the system of arrows. And they are named here the morphism of objects. So they are really the arrows in the topos, not the arrows in the base category. Okay? And so what we discover here is something that is not very well exploited for the moment, is that if you look at the full topos, it contains more than ordinary neural networks. In fact, because each time you join information, you have an added freedom. You can not use it if you want. Okay? This is what is done today. But you can use it, and this is a large difference between natural networks that we have in our head and the artificial neural network. Okay? Because each time you have this joining, as I showed before on the slide, in the brain, this is an entry of something which comes from the brain itself. And this is called spontaneous activity, and it is 90% of the activity of the brain. For the moment, in a neural network, artificial neural network, it is 0%. Okay? So there is a progress to do at this place. But you also something more happened. You have a role of internal geometry. For example, the example 1, which is named CNNs. This is convolutive neurons, and this produce produced in the past a revolution. Backpropagation was a revolution, but also this convolution, because this simple fact that you look at this convoluted transition from layer. For example, in the talk of Carlos Simpson this morning, we saw you have first a set of CNN layer, and this is because you want to detect image, and this is because this property of images is almost a definition what is an image. It is something which doesn't change if you translate. For example, if I am interested by you or look, I'm not really interested by where it is in space. So this seems very little, but it makes really enormous progress. And as you will see, this is in some sense the main interest of the approach I showed you. And it was already present in the work with Berthoz, that all that is done to exploit symmetries. And these symmetries, they act in the over the category or in the topos through the inner spaces. That is, you put at every point of the graph, I show you, in fact, you put a true space. That is, it says that the activities of the neurons at this place speaks of something. And this something is mainly characterized by the group or other structures. It's not always a group, as we will see, which acts on itself. And of course, the transition, which is a dynamic, has to preserve this symmetry structure. This is why you have convolution. That is, convolution is the operation of functions, which makes that you transform translation into translation. Other examples are more hidden. The example 3, perhaps, is not so hidden. It is a different kind of action. You forget about groups, and you take the opposite of groups. A group is a sort of category where you have one object in the graph, and you have many loops. So here it's the opposite. In a tree, for example, you have many vertices, and between two vertices, you have at most one arrow. So this is totally opposite from a group. But this, in fact, this is very similar, and it was the idea of the inventors of category, which were Eilenberg and MacLean, when they invented category for completely other things than what I say here, but connected to algebraic topology and algebraic geometry. In fact, they observed that they are generalizing groups. And what they envisage that the whole theory of category, so including, for example, topos, etc., is a sort of enormous generalization of Galois theory. And the example is the hierarchy. For example, if you take a hierarchy, you have a tree. Now, you can organize the layer of your networks by this kind of hierarchies, or more generally by graph. This gives what is named graph networks, for example. And this can be seen as a new sort of symmetry. Of course, this is symmetry. You say it's not true because it stops immediately. But it is like that in many cases. For example, if I take my arm and I move my arm, I go from one point to another point. I cannot make a complete turn. So I go. I have kind here also of hierarchical structure inside. But you have also more hidden action, also forming stacks, which give you this kind of thickening of of the seats, then of the topos, because after that we will take sheaves over the stacks, because you continue to look to activities which are function. And it is named LSTM. Today, it is mostly replaced, but not totally, by transformers. For example, the self-attention moduli that we saw mentioned this morning, which is a very apparently strange structure, but it emerged from translation problem between two languages for replacing RNN of LSTM, which were not sufficient, which gave enormous structure. And so this was kind of simplification. And this also can be seen, this is an hypothesis mostly at this time, an action of a category on the layer. And this is the design of the network, which is just one cell of an LSTM RNN represented with the picture of site and topos that I just mentioned. Okay. And what is important here, it is not totally apparent, but if you look at the formulas of the transformation, because it is a transient dynamic also. So you have the input, the output. Okay. And so when you look at these trends, what you see is different than what you see usually in a neural network, which is nonlinearity applied to a linearity. Here it is nonlinearity applied to some multi-linear cubic core. That is, you have a cubic operation, okay, which is where you have the three factor, okay, are name, value, okay, and queries. Okay. But here, in some sense, of course, the structure is a bit more precise, but the main property is that this is cubic and homogeneous. And in the theory I developed with Jean-Claude Belfior, okay, that we try to generalize to the thing, okay, you have this hypothesis. That's the fact. This structure, this is LSTM. Yeah, okay. Why? Because it's a structure was used during 30 years. Yeah. So 30 years in this domain of AI, it's not small. Okay. That it tells that this structure, okay, is in some sense almost as important as a linear matrix. Okay. And so it has certainly a structural explanation. Of course, if you look at papers on LSTM, you see a lot of explanation, which are not the one I show here. Okay. And this is in this degree 3, and mainly it reflects this property of the fact that when you look at something of degree 3, even very simple degree 3 polynomial of one variable, okay, you see a very interesting phenomena. That is, you have a bifurcation. Okay? That is, this bifurcation is that you can suppress the roots of the equation f of x equals something, okay? Or you can add them. All of that is better understood on the complex domain, okay? And this complex domain is a good way to represent the Galois group of the equation, okay? And in a sense, this is a figure of ambiguity. This ambiguity here, if you take the true group, which it is not really the group of permutation of things, the Galois group, okay, it's even larger. It is a group which, not by hazard, is in fact is a group of the complementary of a trefoil, okay, of a knot, okay, which is a three-strand braid group. Okay. And so this gives a category which is not given really by a group, because you have at least 3 or even it's better 4 objects. So it's a mixture between graphs and groups, which is named a groupoid. So I could explain better how it happens. But what is important in the sense is that you discover that the translation, which are used by say through CNN for image, okay, have generalization, okay, which are in fact in the semantic domain. That's the point. Because, for example, I have cited hierarchies. Okay. Hierarchies is something semantic. Okay. It says that I will look first at one aspect, then if this aspect takes this value, I look at another one, and so on. So I examine something through a lens which has a structure. This is done by a language. See, this is not so evident for the corpus translation, but in fact, it's also a kind of language, but we don't see why at the beginning. And here, in fact, it was understood by linguists, in fact, not only one linguist. It is even in Saussure, I learned recently, that to understand better the variation of meaning of simple sentences, you use operation which can be understood only by looking at displacement. That's a kind of moves, the elementary moves that you make in this picture. And so this was known in the sense that this picture is semantic in the sense that it is used by linguists to understand cognitive operation underlying natural language. And now I come to this language. Of course, natural language are very complicated. If we want to have machine which satisfy us, they have to understand natural language. The LLM today, like ChatGPT, understands something. We don't know exactly what, but something. For example, they can detect the context. That is a group correctly, the signification of that. But they lack a kind of notion of common sense, and you know very well they make errors that even the baby doesn't make. So, of course, they have an incomplete semantic, but certainly they have semantic. So a language is, what is the name of category, 18 category, is like a Boolean algebra in some sense, where you have inclusion, you have this operation of and, of or, and a negation. And in fact, this kind of algebra are pletors in the domain of topos and stacks. Because they describe what happened for, in some sense, injective arrows between objects. So, for example, the kind of arrows you get for learning, if it is a way to embed something in another thing, I say I have a sub-object, an object, and the way they behave, it is like in Boolean competition, is described by this kind of language. So, in some sense, we introduce now a third level. That is, you have to understand, we try to understand the link between the activity and language. And we saw that a good way to represent structures over inside the network, in some sense, I say over, but C is only the visible architecture. Just transformed by forks. And F is more, because here the points, which are nothing in the category domain, now are spaces. So they are very rich. And the maps are much more. And even you can put, of course, a topology on this side. And on that, now I take a kind of function in the sheet, and in this sheet, which is an element of the topos, I can choose, it is like an object, okay? It gives me a language, at least the logical part of the language. Now, if I take more parts, for example, of the topological space or geometrical space here, I see it appears more than logical operation. Okay? But it appears division, which gives, for example, the types, different types I need in my language. Okay? So, and the type, for example, I am speaking of numbers. It is one type, but I could say I am speaking of spaces. It's not numbers, so it's something different. In mathematics, this is another type. And it appears that certain natural hypotheses, in fact, that you can do, you can impose to this stack, makes that in this language, the information circle well. Under less hypothesis, the information doesn't circulate well. For example, I make an assertion and I can deduce nothing in the next layer. Okay? So under this hypothesis, if something happens in one layer, it has consequences from the linguistic point of view in the further language. So it is something which is added. Okay? In fact, if I take all this collection of language, I have much more. And under a certain addition, for example, if I have topological space, I take their associated simplicial object, like the singular complex. It is shown that we get something very rich, which is kind of Martin Löw theory. In fact, we can get more. We can get what is the interest of informatician today in theoretical information, which is homotopy type theory. And the connection with homotopy was known a lot before. So I was not aware. But in this paper, Simpson-Telemann, 97, which is not cited in your paper, okay, rather exactly one of the points which is important. Okay. So my apology. So in our paper, we make all this description abstractly in themselves as constraints for language, which could be adapted to the dynamic. But they were missing something very important, okay, which is what is the mechanism, okay, which makes that the neurons, okay, understand this kind of language, okay, and can form expression in it, okay, which appears, for example, in LLM. It must correspond to something. I will show an example, and I will stop after this example. And in a few minutes, we need a kind of correspondence, okay, which is very reminiscent of algebraic geometry, between some subsets of activities, okay, and some assertions, okay, which form, for example, what is named theories in a given language. That is, you take a proposition, and every proposition which can be deduced. So from this first paper, we have prepared the second paper, which doesn't solve really this problem, but which give hints, at least, or example where it is naturally solved. And it was not apparent at the beginning, but what happens is that in a lot of cases, in fact, we were not aware that the activities of the neuron and the weights, okay, have more structure. For example, there are analytic varieties, okay, which are stratified. Okay. It is exactly what happens for the transformer. Okay. And they themselves form a stack. Okay. That is, their space have a kind of geometry. Okay. And in some cases, they satisfy the spaces, the hypothesis of circulation of information. For example, there is a generalization of that. It is our main conjecture, already present in our first paper, that the emergence of a language inside a network, okay, could be of cohomological origin, okay, due to a phenomenon that computes the relative cohomology of spaces, okay, when you have a stratified maps. Okay. And in a sense, okay, this natural internal language, okay, which comes from the activities themselves, correspond to taking the derivative dynamics in homotopy. That is, from this kind of geometrical objects, okay, you can have a kind of homotopy, and this homotopy, because of the construction I mentioned, okay, has a connection, direct connection to a language. So, of course, in task, this inner language, this is one of the difficulties. It has to be coupled with the external, with the language of the observers to understand it. But all that would be nice philosophically, because algebraic topology, Abelian or not, is the tool for transforming obstruction in new math objects, which are in some sense more universal. And fundamentally, a neural network, whether it's natural or artificial, is made to create structures, or to detect structures, which is the same, in some problems from particular solution seen during training. Okay? So he does that. He transforms problems, okay, that things which are not evident, okay, in something which is solved. So I present you now the example, which is very, very simple example that we had at the time of publication of the first paper on this topos and stacks, okay? And which is a very simple network. You see, it cannot be more simple because you have, in some sense, two sources of information. Here you have three sources. Okay? So that I don't find the picture in front of me too, where you have a red bar and you have red points and green points. Okay? And now you will analyze that to understand the topology of the configuration. Okay? Do they intersect? Do they are embedded? And so on. And what we observe is that if we take two hidden layers, for example, the network works well and it answers correctly because it's just a problem of approximation. And he solves the problem as an approximation. He do, for example, on the circle here, he do really a Fourier analysis, okay? Like a Fourier series. Okay? And this is the fact. Okay? This is the first change, because the first invariant of the network, okay? The number of layers. We add one layer. Okay? So we have now three hidden layers. And with four, it's even better. And what we observe, okay, is this transition. With one or two inner layers, we do analysis and it solves the problem 99%. But with just one layer more, the cells become discretized. That is, they react by telling -1 or +1, so they are between -1 and +1. Okay? And they do logic. Okay? That is what we observe. Okay? How they do logic? We observe, for example, between the layer 3 and the layer 4, okay, how are made the weights, okay, to make the conclusion, because the conclusion was already correct. But now we understand, okay, how they do. Okay. In fact, they really, what they do is, in the layer 3, the cells are hesitating. So they say perhaps there is an intersection here, or perhaps there is an embedding here. They don't know. But what they do is that they group minimally. By group, in fact, in general, you need 3 such imperfect cells, and to have a cell which concludes. So you have an emergence in this network of logical operation. So no, it's not really semantic in the full sense, but still it is a transformation which appears in the structure on the networks, and which makes that by just adding one layer to the architecture, you create a kind of geometry in generalized sense in the layers. In fact, the idea to do this experiment also comes from neuroscience. It was an experiment of neuromyologists and Moshevakis, which tried to understand how it's possible that you have neurons, like the celebrated neurons, which represent a place in front of the animal, here it's a monkey, in the same manner when the animal is asked to point with the finger, or if he had to look at. So in some sense, this is an inner representation of the plan in front of the animal. But they have to transform that to execute the motion, the movement. So they have to destroy the ambiguity. And they had the idea to construct a simple, very simple layer. It is not exactly the same problem that I show here. And they understood that you have logical operation. And the last part that I will not develop it because it's time. Perhaps I prefer if there is a question about this approach, is to develop the analog of what was done with Pierre Baudot for the entropy in the case of semantic. And the main idea is to see probability law in a Bayesian network as a candidate for theories. And so we take theories and we take function of theories. And now we have exactly the operation in language, small kind of language that we have for variables that we can make a join, which is and. You can negate, and you have, in fact, something which was already interpreted by logicians as a conditioning, which is the implication. That is, if we say, if you look in logic at this formula, so Q is a proposition, R is a proposition, Q implies R is also a proposition. In Boolean logic, it is this proposition, R or non-Q. In fact, it always exists in the kind of language and topos that I have shown, which are small language. Yes, it is a language, sub-object language. And this is seen as conditioning R by Q. This can be understood. And when you do that, you can, for very simple language, compute, in fact, Shannon information, entropy into is 0. So to have non-zero objects, we have to say that this language exists over a geometrical space in the generalized sense I have shown before. And in this case, using this internal symmetries, you can compute the semantic information. So I'm sorry, I will do something which is forbidden when you show slide. I suppress all the slides. Sure, this is the hierarchies, and I come to a result in some sense, which says that when you look at classification, as done psychologists, This classification can obey rules. These rules can be represented sometimes by this kind of simple language with symmetries. And the observation experimental was that some classifications are more difficult than others. And what we show here is that the relative entropy with respect to the orbit of the classification under the group classify exactly the difficulty to learn. This gives an interpretation of the difficulty to learn when there exist rules. And so this is a case where we can understand the possible use of semantic information, which is not pure logic, because it uses this internal symmetry structures. So perhaps I'll stop.